Wireless chargers are basically magic. After a long day of battling green pigs and Angry Birds, you just place your phone down and bam! When you wake up, it's fully charged. But what's actually happening here? First, let's talk about your phone's battery. Your phone is powered by this black rectangle, aka a lithium-ion battery. Inside the battery, there are three components: the anode, the cathode, and the electrolyte. When your phone tries to use power, the battery's anode oxidizes, releasing electrons. These electrons flow out of the battery to power your phone, while positively charged lithium ions take a shortcut through the electrolyte straight to the cathode. Once in the cathode, the lithium ions react in reduction with a metal oxide like cobalt oxide to form lithium cobalt oxide, and then they just sort of wait and chill in the cathode. But as more lithium ions start to chill in the cathode, the battery's stored energy gradually drains, and the battery begins to struggle to generate the electrical current needed to power your phone. Your phone then quickly alerts you of this impending doom with this dreaded notification, and you quickly rush to plug in your phone. By plugging in the phone, electrons are sent to the anode, which, almost like a magnet, begins to pull the lithium ions back to rejoin them. But in wireless charging, instead of directly pumping in electrons through a cord, wireless chargers take advantage of something called electromagnetic induction to fill your battery. How this works is that wireless chargers have a magnetic loop antenna, which is basically just a fancy name for a bunch of copper wires coiled up. When electricity flows through the coiled wires, they create an alternating magnetic field. Inside your phone, there is another coil of wire known as a receiver coil, and when you place your phone on the wireless charger, the magnetic field from the charger causes electricity to flow inside the phone's coil. The larger the coil and the more coils there are, the stronger the magnetic field and the more energy can be transferred wirelessly. But not all the energy is getting through right now. Some of it is being lost to something called impedance mismatch. Impedance is the total resistance to the flow of the current. And if the impedances in the transmitting and receiver coils aren't in sync, some of the energy is reflected back or wasted as heat in the transmitter circuit. But if the two coils are tuned to the same frequency, in a phenomenon called resonant inductive coupling, the reactive components of inductance and capacitance cancel each other out. This minimizes impedance and can increase the energy transfer efficiency to over 90%. And to help keep things practical, most wireless chargers use something called the Qi standard. This is sorta like a universal language for wireless charging. It's backed by tech giants like Apple, Samsung, and Google, ensuring that nearly all smartphones are compatible with Qi chargers. Plus, the Qi standard focuses on minimizing energy loss during the wireless power transfer, hoping to reduce waste and heat. Although the original Qi standard only supported power levels up to 5 watts, today's current standard supports up to 15 watts, with plans to support up to 60 watts. That means faster, more efficient charging in the future.